it's 1 over 2i, the commutator of a and b. And of course, the commutator of a and b, or ih bar lz, oh, there should be an lz here, sorry. So, we get something like this, which is unfortunately very, very sad. So, we can't do anything about that. Can we find two quantities that are compatible? Well, the next optimal guess is to try the magnitude of L, or the norm. But you quickly realize that, what is this going to give you? The square root of Lx squared plus Ly squared plus Lz squared, which would be fine if they're scalars, but they are operators. Now, we've spent hundreds of years trying to figure out what this thing means to no results. So imagine what would happen, well, not to no results. There are a lot of results on fractional calculus. But imagine what would happen if we tried to mush multiple of them along with some non-operator coefficients under a square root. All hell would break loose. So instead of doing that, our next best idea is to try L squared. At least that doesn't give us a nasty square root, and the squared terms are easy to define. They're just what happens when you apply an operator twice. So, is the norm squared of L compatible with any one of the components? Well, we have to test it. Oh, no, this is the right black. So, let's test it with Lx, and then we can use cyclic permutation once again in order to get Ly and Lz. So the commutator of L squared with Lx is what? Since L is a linear operator, like every single operator we're going to see, this gives us Lx squared Lx plus Ly squared Lx plus Lz squared Lx. Notice how I'm not drawing the hats, because that would be one too many hats. We get Lx cubed minus Lx cubed for this term, and so we get 0 here. Then what do we do about these other two? Let's first write out what these even mean. Consider that a squared in b is equal to a squared b minus b squared a. Oh, sorry. Now, it's